This is Business Calculus 1, Section 5.4 on graphing, revised and finalized.
This is a recap of lecture on Section 5.4 from last Tuesday.
So here we're given a function f of x as before, and you find f prime and f double prime, simplifying if appropriate. And then we do everything we did in Section 5.2. That is, you have a four-step method. The first step is to look at the f, and you find all x and y intercepts, note the domain, and what's new here is that you find the horizontal and vertical asymptotes. The second step is the same as before. You'll analyze f prime and make a sign chart for f prime, and that gives you local extrema. Third step is you do what we did before in Section 5.2, and then you find a sign chart for f double prime, and that gives you concavity and inflection points. Now you sketch the graph or identify it on a multiple choice problem by taking into account the information from steps 1 through 3, possibly with the assistance of a graphing calculator. Here's the first example. Let's sketch the graph of f of x equals x over x minus 2 using the method above. First, notice that the y-intercept is f of 0, and that is 0 over something, and that gives you y equals 0. The x-intercept is gotten by setting y equal to 0, and that gives you that the numerator is 0, namely x is equal to 0. Recall that a fraction is equal to 0 if and only if the numerator is equal to 0. Now we know that the graph goes through the origin 0, 0. That's x equals 0, y equals 0. And we know that the domain is all x not equal to 2, because we just have to avoid the value where the denominator is 0. Okay, so it's all numbers except for x equals 2. The vertical asymptote is the line x equals 2. Okay, so it is not just 2, it is the equation x equals 2. The horizontal asymptotes are gotten by taking the limit as x goes to plus or minus infinity. Okay, and by the leading term method, also by L'Hopital's rule, but more simply by the leading term method, you look at the leading term, which is just x over x on the top and the bottom. Okay, so you can just sketch that by isolating the top and the bottom there. And so the horizontal asymptote is the line y equals 1. So for the function x over x minus 2, the second step is to look at f prime, which is gotten using the quotient rule. So we have the derivative of the top, which is 1, times the bottom, minus the derivative of the bottom, which is 1, times the top, which is x, all over the bottom squared. So just leave that bottom squared like that as x minus 2 quantity squared. You simplify the top as x minus 2 minus x, which just gives you minus 2 over x minus 2 squared. And you want to check this in your own notes that you get exactly that. Since the bottom is a quantity squared, the bottom can't be negative, so this function, this f prime, is negative for all x except for x equals 2. So it's negative for all x not equal to 2. The partition numbers for f prime, remember that's where f prime is 0 or undefined. Well, f prime is never 0 because the numerator is 2, which is not 0, and the f prime is undefined at x equals 2. So that is the single partition number. So here's the sign chart for f prime. Well, you look at f prime and, well, it's negative except for where it's undefined at x equals 2, and it's negative also to the right there. So f prime is negative, and therefore decreasing on the two intervals from minus infinity to 2 and from 2 to infinity. So the function f is decreasing on its entire domain. Therefore, there are no extrema. Next, in the third step, we compute f double prime, and f prime is written as, or rewritten as, minus 2 x minus 2 to the minus 2, okay, using negative exponents. So this used to be in the denominator as x minus 2 quantity squared. You differentiate this again, and the fastest way to do this is not by the quotient rule, even though that works, but it is to use the power rule. So the minus 2 comes downstairs, and you get plus 4 in the front, and x minus 2 quantity to the minus 3. So that is 4 over x minus 2 cubed, which is what you'd get if you use the quotient rule on the original form of f prime. So f prime can be written as 4 over x minus 2 quantity cubed. The partition number for f double prime is where it's undefined, it's never 0, and that's at x equals 2 again. So here's the sign chart for f double prime. The sign is determined by x minus 2, since when you cube x minus 2, it retains the sign. So if x is less than 2, for example, if x is equal to 0, you get a negative number cubed on the bottom, and it is negative. To the right of x equals 2, it is positive. For example, if x is equal to 3. Okay, so f is concave down from minus infinity to 2, and concave up from 2 to infinity. Therefore, you can summarize this by saying that f double prime is positive, and therefore f is concave up from minus infinity to 2, and concave down from 2 to infinity. Again, the simplest way to determine the sign of f double prime is just to look at the factor x minus 2, which appears as the cube in f double prime. The concavity never changes, so there are no inflection points. And here is the graphing calculator sketch of this function. Some features are that, well, f has both its x and y intercept there at x equals 0 and y equals 0, the origin. The asymptotes, which were gotten by looking at limits, well, the horizontal asymptote is y equals 1, and the vertical asymptote is x equals 1. Okay, so I sketched those in on top of the graph. The function is decreasing from minus infinity up to 2, and it's decreasing also from 2 to infinity. By step 3, we know that the curve is concave down from minus infinity to 2, and then it's concave up to the right of x equals 2. So your graph reflects the concavity, i.e. the sign of f double prime. And that's the end of the first example. Here is another example. Let's sketch the graph of f of x equals x times e to the minus 0.5x. Note that that 0.5x can be written as 1/2 x, or x over 2. The y-intercept is always gotten by plugging in x equals 0, and when you plug the x equals 0 in, you get 0 times something, and that's 0. So the y-intercept is y equals 0. The x-intercept is gotten by setting x e to the minus x over 2, the function, equal to 0. And that gives you the first factor, x equals 0, right? And e to anything is always positive and therefore non-zero. So you can ignore that in solving this equation. And we're going to use that fact about e to the x repeatedly. So the x-intercept is x equals 0, and the graph goes through the origin 0, 0. The domain is all x, right? E to the x is always defined. Okay, so it's x over e to the 0.5x. All right, and as x goes to infinity, this is of the form infinity over infinity. By L'Hopital's rule, you can take the derivative of the top, which is 1, and then the derivative of the bottom is 0.5. That's the derivative of u, the exponent u, and then you get e to the 0.5x on the bottom. So I've taken the derivative of the top and the bottom independently, and I get that. Now there's only an x in the denominator here, so that is a basic limit where the denominator goes to infinity and the numerator stays at 1, so the value of the limit is 0. Therefore, y equals 0 is the horizontal asymptote. Moving on to step 2, we find f prime, and that uses the product rule. And so you take the derivative of the first factor, which is 1, times the second factor, and here I've just written 0.5 as 1/2, so you get minus x over 2 as the exponent, and then you have the derivative of the second factor, which is minus 1/2 e to the minus x over 2 times the first factor, which was just x. So taking this expression, as we have several times in the past, you factor out the exponential term. So when you do that, you get a 1 from the first term, and you get a minus 1/2 x from the second term. So it's 1 minus 1/2 x quantity times e to the minus x over 2. Therefore, the partition numbers for f prime, that is the critical values for f, is x over 2. There's just that one critical value. Notice that you can ignore the exponential term because it's never equal to 0. This is always strictly positive. So you really only have to deal with the factor 1 minus 0.5x. So here's the sign chart for f prime. It is determined by the factor 1 minus 0.5x. So to the left of x equals 2 is positive, for example, at x equals 0, and it's negative to the right of x equals 2. So f is increasing up to x equals 2 and decreasing to the right of x equals 2. Thus, f is decreasing from 2 to infinity and increasing, where f prime is positive, increasing from minus infinity to 2. Therefore, there is a local max at x equals 2, and the local max is, by plugging 2 into the original function, 2 times e to the minus 1, or just 2 over e, and that is approximately equal to 0.7422 decimal places. So from the previous step, we have f prime equals 1 minus x over 2 e to the minus x over 2. So calculating f double prime using the product rule, we get that the derivative of the first factor is minus 1/2. That's the coefficient of x, it's minus 1/2, times the second factor, which is e to the minus x over 2, times the derivative of the second factor, which is minus 1/2, that's the coefficient of x in the exponent, times e to the minus x over 2, times the first factor, 1 minus x over 2, or 1/2 x. So make sure you can walk through that and see where we got each of the terms here. Okay, and you can simplify this now to 1/4 x e to the minus x over 2 minus e to the minus x over 2. where the 1/4 comes from combining the minus 1/2 e to the minus x over 2 times minus 1/2 x. And the second term comes from minus 1/2 e to the minus x over 2 times 1. There is an alternate version for computing f double prime where you multiply out f prime first, but I won't expand on that right now. But there is an alternate version. Okay, the partition numbers for f double prime are gotten by ignoring the exponential factor, and you just get 1/4 x minus 1 after you factor f double prime, and you get x equals 4. Here's the sign chart for f double prime. The partition number is x equals 4 in the middle there, and then the sign of f double prime in its factored form is determined by the factor 1/4 x minus 1. So for example, if x equals 0, it is negative. And then it's 0 at x equals 4, and it is positive if x is greater than 4. Therefore, f is concave down until you hit x equals 4, and then it's concave up. In chart form, it says that f is concave up on the interval from 4 to infinity and concave down from minus infinity to 4, to the left of 4. Since the concavity changes at x equals 4, you have the inflection point, the IP, at x equals 4, y equals f of 4. So that point on the graph is 4 over e squared, which is approximately the 0.4, comma 0.54. The detail on that computation for f of 4 is gotten by plugging x equals 4 into the original function, so you get 4 e to the minus 2, which is the same thing as 4 over e squared, which you calculate to be 0.54 to 2 decimal places. Often you'll just be asked for the x coordinate, x equals 4, in this for the inflection point. Here's the graph of f of x, which was x e to the minus 0.5x. Okay, the max, or the local max, was at 2 over e, so that is the first blue dot there. And then the inflection point was at 4 over e squared, and remember the y-coordinate was about 0.5 there, so you can see how that matches up to the graph. The function is increasing up until x is equal to 2, up until the max, and then decreasing to the right. It is concave down until x is equal to 4, and then it is concave up. There are no vertical asymptotes, and we saw that there is a horizontal asymptote, namely y is equal to 0. So you can indicate that with a dotted line along the x-axis. When you graph this in a graphing calculator, you have to make sure that your y-scale is small enough so you can actually see the way the curve is shaped with the local max here and the inflection point here. Let's do one more graphing example. Let's take a look at log of 1 plus x squared. Since 1 plus x squared is always greater than or equal to 1, this function is defined for all x. Even if x is negative, 1 plus x squared is a positive value, so you can take the log of it without being undefined. Therefore, the graph goes through the origin 0, 0. So 0 is the x-intercept and is also equal to the y-intercept. Since the function is defined for all x, there are no vertical asymptotes. If you take the limit as x goes to plus or minus infinity, well, log of a larger and larger number is an unboundedly large number, therefore the limit is infinity. Therefore, there are no horizontal asymptotes. The derivative is given by u prime over u, the chain rule for log of u, and that's 2x over 1 plus x squared. Okay, so the critical value here, well, the denominator is always bigger than 1, so the only critical value is at x equals 0. That's where 2x is equal to 0. So you see the sign is just determined by x itself and ignoring all other positive factors. So here's the sign chart. Here it's positive if x is greater than 0, and it's negative if x is less than 0. So the local min here is f of 0 equals 0 at x equals 0. Let's move on to f double prime. F prime, as just above, was 2x over 1 plus x squared. So we have to use the quotient rule here for f double prime. So we're going to strip off the factor of 2, and then the top factor has derivative 1, which we won't write, and then we have 1 plus x squared, minus the derivative of the bottom, which is 2x, times the top, which is just x. And the whole thing is over the bottom squared, so you have 1 plus x squared, quantity squared. This simplifies to 1 plus x squared minus 2x squared, or 1 minus x squared on the top. Now for the partition numbers for f double prime, well, the denominator is always positive, so the sign is determined by 1 minus x squared. Therefore, the partition numbers are at x equals plus and minus 1. So here's the sign chart for f double prime. In the middle here, say at x equals 0, you get 1 minus 0 squared, so it is positive. And to the left and right, if x is a big number, you get a negative f double prime. So you have the concavity as shown. It's concave down from minus infinity to minus 1, concave up from minus 1 to 1, and concave down again from 1 to infinity. And you have inflection points at plus and minus 1. Plugging in plus 1 and minus 1 into the function both give natural log of 2. So there's the y-coordinate on the IP. Here's a rough sketch of the function. Notice that it's concave up from minus 1 to 1, and there is a local min at x equals 0. That 0.7 is the approximate value of natural log of 2. Of course, you can replicate this graph on your graphing calculator.
Let's start 5.5 on absolute extrema, starting with the definition. If f of c is greater than f of x for all x in the domain of f, then f of c is said to be an absolute maximum or absolute max for f of x. Absolute minima are defined similarly. In these cases, we have that the function f of x has an absolute extremum at x equals c. And this means that in the case of an absolute max, this means that the f of c is the largest function over the entire domain of f. And an absolute minimum is the smallest value of the function over the entire domain. Contrast these with the relative or local extrema that we had before, which were just maxes and mins considering nearby values, not the entire domain. In general, absolute extrema, maxes and mins, occur at local extrema, that's peaks and valleys, or at endpoints of the domain. Anytime you have a closed interval, there's always an absolute max and an absolute min on that closed interval. However, if you have open intervals, say from 0 to infinity without endpoints, you may not have an absolute max, or from infinity to infinity. And of course, local extrema may not be absolute. For example, in the function shown here, you have a local max here, but there are bigger values over here, so the local max here is not an absolute max. And similarly, this local min is not an absolute minimum since there are smaller values over here. However, local extrema are good places to look for absolute extrema. In this bell-shaped curve on the left here, the local max here is the max overall. In other words, it's the absolute max. Next, we have a very useful theorem called the second derivative test for absolute extrema. Suppose you have a continuous function on an interval, an open or closed interval, with a unique critical value. So that's a value in the domain inside of this interval where the first derivative is either 0 or undefined. In two cases now, if f prime of c is equal to 0 and f double prime is positive, then f of c is the absolute minimum on the interval. If f prime of c is 0 and f prime of c is less than 0, then f of c is the absolute max for that interval. In this statement, we only cover the case where there's a unique, that means one and only one, critical value in the interval. You should have in mind a picture like this. In this case, f prime of c, here c, is equal to 0 because it's a horizontal tangent, and f double prime of c is negative, meaning the function is concave down over the interval, and this point here is the only critical value over the interval pictured. Then here f of c is the absolute max. Okay, so it's the only critical value, and the concavity pictorially tells you that you're talking about the absolute max. In the example on the right here, you're talking about a function defined for all x from minus infinity to infinity, and here you have a unique critical point, and it is the absolute minimum. The curve is concave up, and there's a horizontal tangent at this value c. So f of c is the absolute minimum in this second case, corresponding to the first case, the concave up case in the theorem. Overall, this gives you a very useful way of finding absolute extrema. You look for the case where there's only one critical point, and then you use the concavity to detect whether you have a max or a min. Notice that we're only addressing the case where f prime is equal to 0, and that's the unique value for which there is a horizontal tangent. And that value x equals c is the unique critical value in this theorem. Here's an example. F of x is x plus 4 over x, defined only from 0 to infinity. So that's the interval of definition, the domain of the function in this case. F prime of x is 1 minus 4 over x squared. Here the derivative of x is 1, and the derivative of 4 times x to the minus 1 is minus 4x to the minus 2, or equivalently minus 4 over x squared. Okay, as you recognize because you know the derivative of 1 over x. While we're at it, f double prime is equal to, well, the 1 disappears and you get minus times, and then you have an exponent of minus 2 here, so that gives you minus 4 times minus 2 is 8 times x to the minus 3, or 8 over x cubed. To find the critical values, you set f prime equal to 0, and you get 1 minus 4 over x squared equals 0. That immediately implies, by multiplying both sides by x squared if you like, or solving some other way, you get x squared minus 4 over x squared equals 0. And then factoring, or otherwise, you get x equals plus and minus 2. Don't forget about the minus 2. But because the domain is just positive values of x, that reduces to x equals 2. We throw out x equals minus 2 because it's not in the prescribed domain. So there you have a unique horizontal tangent. It's the one and only one place where f prime is equal to 0. So it's the unique critical value, as in the hypothesis of the theorem. Now let's look at the concavity. F double prime at this unique critical number is, well, it's f double prime of 2, but that's just 8 over 2 cubed. Whatever that is, it's a positive number, 8 over 2 cubed. Okay, so that is a concave up situation because of the sign of the second derivative at 2. According to the theorem, then, you have this unique critical value in a concave up situation. It says that f of 2 is the absolute minimum. And we can reiterate that we're only concerned with x positive in this problem as stated. given the domain over the interval from 0 to infinity. Again, here you should have in mind the picture where you have a horizontal tangent and the curve is concave up at that horizontal tangent, and that corresponds to an absolute minimum for the function. This conclusion only applies when you have a unique critical value, but that's a very common situation, as occurs here. Here's another example, which we more or less did before in section 5.4, but here we have the function f of x equals 1 over x squared plus 1, and it's defined on the interval from 0 to infinity, this half-open interval with the endpoint at x equals 0 included. So we'll whip through the computations because we did them before in class. F prime is minus 1 times x squared plus 1 to the minus 2 times 2x, thinking of this as u to the minus 1. And there's a minus sign in there, so it's the overall derivative is minus 2x over x squared plus 1 squared. Again, we got that using the power rule for the original function. F double prime of x is equal to, okay, well there it is using the quotient rule, and again, you can walk through that. That's unsimplified, and we did this in class, so I won't go through it again. But the beauty of the situation here is that, well, we can ask, where is f prime equal to 0? When do we have a critical value? The denominator is always positive, so we don't have to worry about it being undefined, but where is this derivative equal to 0? Well, it's when x is equal to 0 only, when the numerator is equal to 0, or 2x equals 0 implies x equals 0. So we have the unique one and only one critical value, x equals 0, and there f prime of 0 is 0. Moving to concavity, f double prime of 0 is equal to, well, you're just plugging a 0, so you're just going to use the unsimplified version here. Anytime you have an x factor, this whole term is 0, so you just get 2 times 0 squared plus 1 squared, that's just 2. And this whole thing's over 0 plus 1 to the 4th power, so overall, by plugging in x equals 0 into this expression for f double prime, gives me minus 2 pretty quickly. And so that's a concave down situation. So what does that tell you? Well, it says that if you just picture this, that f of 0, which is equal to 1 plugging into the original function, is the absolute max. Again, you think of the shape, horizontal tangent plus concave down suggests an absolute max. And the theorem says that is the absolute max for the function. Here defined on this half line. As I said, we did simplify this f double prime by factoring out the x squared plus 1, and in case you missed that or want to see it again, here it is on the slide, so you can pause here and look at the simplified factored form of f double prime, even though that's not required for finding the absolute max. And here's what the graph looks like for the entire line, and what we just found was the absolute max f of 0 equals 1. Whether the function is defined on half the line from 0 to infinity or the entire line. You have the absolute max, f of 0 equals 1, which is said to occur at x equals 0. In section 5.6 now you have the following example, which involves maximizing area. A rancher wishes to spend $320 building a fence to enclose a rectangular region. 3 sides of the fence cost $2 per foot, and the 4th side, the expensive side, costs $6 per foot. Find the dimensions of the largest area that can be enclosed. So we want to maximize the area under these constraints. You want to draw a picture with the variables labeled. So you just have a rectangle with 3 of the sides being $2 per linear foot and the top being $6 per linear foot. So draw this picture on your own, and we want to maximize the quantity x times y. And the constraint from the picture that you have is that we had was 2x plus 2y plus 2y
those are the three sides that cost $2 per foot, so there's the total cost, plus the top, which is costs 6 times X, and that's equal to 320. That simplifies down to 80 minus 2X equals Y. So Y is solved in terms of X, given this constraint that stayed in the problem. So now you have the function for the area, A, is the function which we call f of x, is x times y, and that is now x times 80 minus 2x. The point is that you no longer have a y in the equation. This is xy, which is this expression, which is now 80x minus 2x squared after multiplying through by x. And this function, A equals f of x, is the function that you want to maximize. Take note that the domain is x and y are both greater than 0, and what that means is that x is between 0 and 40, thus the open interval 0 to 40. To find the critical number, you look at f prime, which is 80 minus 4x, differentiating f of x, and that tells you immediately that x is equal to 20. And f double prime is minus 4, so you're in a concave down situation at this critical value. So the second derivative test for absolute extrema says that there's an absolute max at x equals 20. And that basically answers your question. If x is 20, then y, using the equation 80 minus 2x, is 40, and the area is 20 times 40. So the maximum area is 800 square feet, and that occurs for a rectangle that is 20 by 40. And that completely solves this maximizing area problem. Now we have a couple more examples from 5.6, the last section, and here's an example out of the book. The price-demand equation for, say, toasters is given to be P equals 300 minus X over 30. What price should the company charge to maximize revenue? So we want to maximize the revenue function in this case, and you might recognize that we've seen this problem before. If the cost of producing X units is C of X equals 90,000 plus 30X, so there's the cost function, find the maximum profit. So the first question is this, well, let's maximize the revenue. R is Px as usual, so that's X times, and then P was given to be 300 minus X over 30, so the product here is the revenue function. Multiplying out gives me 300x minus 1/30 x squared. Now we want to find the maximum, which is the vertex of that parabola. Well, r prime is easy to find using the multiplied out form. 300x gives me 300, and you get the 2 times 1/30 gives you minus 1/15 x. Okay, and you set it equal to 0 to find the critical value. As a polynomial, so it's always defined, and you solve this equation and you immediately get 15 times 300 is 4,500 units. So that's your candidate for the absolute max. It's the unique critical value, but in the situation, you know this must give you the absolute max revenue. There's no such thing as minimum revenue. So that's it. The max revenue occurs at x equals 4,500 units. And that's simpler than finding the vertex of the parabola, even though they're both pretty easy. Note also that r double prime is minus 1/15. It's a constant gotten by differentiating r prime, and that's always negative, so you're in a concave down kind of situation, and that reaffirms that there is an absolute max at that critical value 4,500. Okay, so that's a backup fact in case it wasn't clear to you already. So again, you can use r double prime to decide whether there's a max or a min at the critical value. Now, to actually answer the question, at that critical value 4,500, P, which is this factor right here, is 300 minus 4,500, that's x equals 4,500 over 30. Okay, so you've plugged the critical number into the price function and got the price, that's $150. So that's the price that produces the maximum revenue. That's where you'd want to set the price to get the revenue to be as big as possible. So that's the answer for the first question.
Moving on to the second question of maximum profit, let's write down the profit function. So that's a quadratic. Remember, it's r minus c. That's the profit function. So 300x minus 1/30th x squared minus, in parentheses, 90,000 plus 30x. That was the cost function given before. So you just add up the terms and you get minus 1/30th x squared as the squared term, and then you get 300x minus 30x, make sure that you distribute the minus sign, and that's plus 270x minus 90,000. So there's the profit function. And we want to find the value of x for max profit. Well, and again, that's the vertex of what turns out to be a parabola here. And now we can use the derivative and solve this problem rather quickly. We get minus 1/15th x from the x squared term plus 270x, and the 90,000 is irrelevant, so there is p prime. And you set it equal to 0 to find the critical value. Okay, and then you get 15 times 270 is 4,050 units, and that's the unique critical value. So that gives you the point where there's maximum profit. Note also, you can just check that p double prime is negative, so you're in a concave down kind of situation. So you have an absolute max at this critical value, 4,050. The maximum possible profit is given by plugging in this critical value. So this absolute max value is p of 4050, and you just plug this in your calculator into the profit function, and I compute this to be 456,750. So that is the maximum profit, or the absolute maximum profit. And it occurs when the price is, well, what is the price? It's got by plugging in this critical number 4,050 into the price function, which was 300 minus x, which is now 4,050 over 30. And that computes out to be 165. So that's the price at which you obtain maximum profit, which is a surely interesting value. So that's the end of this problem, which recapitulates the profit revenue sort of problem we started the course with. Here's a classic problem. The U.S. Postal Service requires that the length plus girth of a box be at most 108 inches. Find the dimensions of the box having square cross-section having the biggest possible volume subject to these restrictions. So you imagine a box having a square base and it's got a certain length. So here is a picture of the box, and for a lot of these problems it's a good idea to picture the problem, and you might imagine the side of one of the box of the squares to be x, and the other side is also x by definition of square, and then you have the length of the box, say z for the length. So the restriction that is given is that x plus x plus x plus x plus z is less than or equal to 108. So x plus x plus x plus x is the circumference of a cross section, and that is what is known as the girth. So keeping in mind that picture, we want to maximize the volume over the interval from 0 to infinity, where again x is equal to y are the side lengths of a cross section, and z is the length. So here's the picture again, and the constraint is that 2x plus 2x plus z, so that 2x plus 2x is the girth, and we set that to be as big as possible, that is 108 inches. Okay, and then you solve this and you get z as 108 minus 4x. That's just a true equation, or the constraint as given by the USPS. Okay, but now we want to maximize the volume, so we have to write down the volume function. What is the volume? Well, it's the product of the dimensions. So what we get is as follows: v of x, the volume function is xyz, but here it's just x times x, that's the base, times the length, which is z, so it's x squared times, and by the previous equation we have z is 108 minus 4x. So we can plug that in. Z is 108 minus 4x, so you get 108x squared minus 4x cubed, and that's the volume function. And we got that using this equation from the previous slide. And now we differentiate that function because we want to find a max for it, and we get 2 times 108 is 216 times x to the first power minus 12x squared. 3 times 4 is 12, x squared. And we can factor this. This is 12x minus 18 minus x, factoring a 12 and an x out of each term. And v double prime, while we're at it, is 216 minus 24x. The critical value or critical number is x equals, well, you solve this and you get x equals 0 and x equals 18, but only x equals 18 counts because x being a length of the side of a box is positive, so you can disregard x equals 0. So there's the unique critical value over the real domain of the function. So it's 18 is the value. V double prime of 18 is 216 minus 24 times 18, and you compute that to be negative. The point is that that is negative, so it's concave down situation with a horizontal tangent at x equals 18, and that theorem, the second derivative test just before, was tells you that you have an absolute max at that value x equals 18. In other words, by the theorem, the absolute max is at x equals 18, and the other dimension of the box, which is also equal to x, or we called it y also, is 18. And z is 108 minus 4x, so it's 108 minus 4 times 18 is 36. So the box is 18 by 18 by 36, and the maximum possible volume is x times y times z, or x times x, which is 18 squared times 36, which turns out to be 11,664 square inches. In Calc 2, you'll do the same problem where x is not necessarily equal to y, and this is why we have x and x equals y here as two different variables. This is the end of section 5.6.